Okay. Write down the time. All right. So let me, oops, I gotta get my phone here. All right, let me let that connect. And once that connects, I'll switch over here to, thanks. Good. And switch over to the questions. All right, so let's try 57 here. It says a material with a uniform resistivity rho is formed into a wedge as shown. Show that the resistance between face A and face B is given by this formula. All right, and so I would describe this one a lot like the one we did before this. What number was that? 52, I believe. Yeah. 52, and then the one you said you just did on your own, 56. And so all these kind of go together. And I'll start with one of the lessons of the chapter was this, that the resistance depended upon 4 factors. The resistivity is actually the material, but it's also temperature dependent. So that's 2 factors right there, the temperature and the material. And then how long is the material, and then the cross-sectional area A. And we have to be careful with this definition of L and A, because those are easily confused. You know, when you're talking about a surface A and you have something that looks like, number 57 or 56 or 52, you're like, well, what surface area are we talking about? And so note that this was derived with the idea, if this is kind of a wire, and the L being the length of it is the direction that the current flows, and then the A is the perpendicular face to that flow, the surface area to that flow. So if we take a little bit of calculus with this and say, well, we could think of this really as a little tiny piece. And so maybe if this is like a stack here of coins. I grabbed the nickels somewhere for just this reason. Maybe I should have grabbed a bunch of nickels. But if I had this wire, I could say, okay, this is a slice into the wire. This is a disc. And this nickel represents one little small piece of it. And the whole resistance then is the integration of that. But what I'm getting at is if I take the differential here, dr, a little bit of resistance, would then be associated with a little bit of length. Now, the reason that's important is because harder problems, the length varies. You could see in a problem like this, that if you just wanted to find the total resistance, you would just add up all the little nickels that made up the stack of coins. And if they all had the same radius, then this would be a pretty easy integral to do. You would get exactly what we just had before we took the differential. You would factor out the resistivity, you would factor out the area, and that's the key step, area being a constant. You pull it out, then you got just an integral of dl, which is the L. And so what I'm trying to say is the same thing I said at the beginning of 52, is let's do this. Let's say that the total resistance is the sum of a bunch of slices, and our slices then, each one has a resistance given by this little formula. That is the resistivity times the microscopic length of it divided by its area. And its length then would, of course, be some kind of small distance in the direction the current is flowing. So if I kind of draw this picture in I'll try a cross-sectional view. And so I'll say this is the face A right here. I'll say the current is coming in face A. And they said it has a height of y1. And it's going to go along this material. And this material gets bigger as it goes along. Kind of has a wedge shape to it. I guess how they define it. They said forms a wedge as shown. And so it's going to come out over here at face B and kind of looking at a cross section. And so again, this would be a height Y2 as it got bigger. And then they say it's going to flow along a length L. Now, if I try to make my picture three-dimensional, the wedge might look something like this, where then over here on face B, they say this is the width of our wedge shape. And what I'm trying to say here is let's use our calculus and take a little piece of this and kind of color it in. And this little piece, the current would be flowing from left to right. And so this DL is actually the thickness of this little slice. If I have this rectangular thing that kind of wedges out, I'm trying to think of what might get a little bigger that you might cut into wedges. The other one was easier. We could talk about a round one, a carrot. Vaguely a loaf of bread on its edge. How about that? You know, so you got this loaf of bread, it kind of tapers down and you're slicing it into slices. And so this is one of the slices of bread. And so near this end, the slice is small, and near this end, it's big. And then, of course, a loaf of bread then has a long section that's about the same height. But there's this tapering part to it. And so imagine this a stack of sliced bread. And
or maybe for consistency, a Post-it note, a single Post-it note, and a stack of glued Post-it notes.
Yeah. Okay. So here's my stack of Post-it notes. I've been using that a lot. The only thing that's lacking in the Post-it notes is they don't kind of taper. Maybe if I had like sliced it across here. Then each Post-it note, as I take it off, gets bigger and bigger and bigger and bigger. But yeah, Post-it note works great because when I do then take one Post-it note off, you can see that it's rectangular in shape. And so that's the part that would be the area that it flows through. So I'm going to use that in this equation and say, okay, here's the integral. And the resistivity is the material. So that doesn't change anywhere. Let me just kind of verify that. It says a material with a uniform resistivity. So it's the same material. But along its length, along the either the slice of bread or the Post-it note here, this thickness would be along, and I'm going to call this then the x-axis. So instead of continuing to call it a DL, I'm going to kind of change it into a mathematical grid. And usually, you know, that horizontal axis is called X. So I'm going to follow that. Call that an X. So that's a DX. And then the area, okay, well, the area, that's where it's important to kind of know what we're slicing. And so this Post-it note works really good. If you kind of tilt it on its side, you'll see it has a length and a width, and that would be its area. Unlike for the break, we were doing that 52. In our Post-it notes, we were doing shells, and I wrapped it kind of in a circle here and said, okay, this is the area. And we unfolded it, and so it had length and circumference. But on this one, each slice then is just rectangular in shape. And clearly with the wedge, the height of it keeps changing. So I'm just going to call it its height for the moment. but its depth, or in this picture, what they call the width, doesn't. And so that's a W. So its area would be H times a W. And then I've got some work to do to figure out, okay, where along on the x-axis am I, and how does that determine its height? Because its height varies. Its width does not, but its height does. So let me just kind of put a pause on this equation for a moment, and let me put a grid on here. And so here's my x-axis, and here's my y-axis. And if I do a cross section again, and I'll start then with this wedge with a height of y1 right at x equals to 0. So here's x equals to 0. And this wedge piece is going to go along the x-axis until we get to L. Hang on a second, let me check something. Okay. See what all that commotion was outside there. Okay, so all right. So it goes a length L on the x-axis. Okay. And then, of course, as we're going along the x-axis, it's getting taller. And that's why I was, taking these Post-it notes, kind of slicing it. And so each one gets a little taller. And at the end, it has a height of y2. And so what I'm trying to say is somewhere here, there is a height, and that height is really kind of along this line. And so if you think about this line, then we just need a mathematical equation to represent that line. So here's where I'm going to fall back to my knowledge of mathematics and say, okay, the equation for a line is y equals to mx plus b, where the m is the slope of the line and the b is the intercept. And in this case, then, the y would actually represent how high it is, and that's the height. So I guess my first step is I'm going to replace the y with an h and just say, okay, that function, this line right here, is the height of my sticky note or my sliced bread. Now, the slope is rise over the run. Okay, so you kind of look at this line. It starts at y1 and gets taller to y2. So the rise would be y2 minus y1. And the run would be how far along on the x-axis did it go. And then the intercept, well, that's where does it cross this line? And looks like this line comes down and crosses the y-axis at y1. So that would give me a nice mathematical equation for what is the height of it. All right, so let me use that back into this equation we did back on page 1. Okay, so then I have my integral, and I've got my resistivity, and I'm going to just kind of change the order here since those are a constant. I'll put my width first, and that's the new piece, this h downstairs. So I'm going to leave the dx upstairs. And then downstairs, I'm just going to put that equation, which is y2 minus y1 over L times x plus y1. And so that is why we have to do our calculus, because the height keeps changing, which makes the area change. Okay. Now on this one, I was going to say maybe we should do a change of variable. Yeah, I'll do a change of variable. Let's do a u sub, but this one we can almost do without a u sub. But I'm going to just do this. Let's say u is equal to, and I'll just put that whole thing, y2 minus y1 over L times x plus y1. So that whole thing is going to be u. So du would be y2 minus y1 over L dx, and derivative of a constant would be 0. Okay, so now doing my integral, put a rho over the w, and so now I can put downstairs just everything, because it's equal to a u. So the whole downstairs is substituted with a u. Now upstairs, I got to put the dx, and so moving the L and the y2 minus y1 to the other side, I get this. So L over the difference, and then the du. Okay, and then like any good integral, to simplify it, go ahead and bring constants out in front of the integration sign. And so that, and that, and that. And then I just have a du over a u, which is ln of u. Which, of course, now I can go back and put in what is the function u. It is y2 minus y1 over L x plus y1. And now the limits of that integration. I was going to say maybe I should have changed my limits of x to my limits of u. That might have been easier. But anyways, I like to go back to the physical thing. So I'm going to go back to the x, because the actual limits of my integration are really easy to see. It's 0 to L. So 0 to L. Okay, so let me just copy down the constants here. All right, so then I would have ln of, and so if you put in an L here, you can see that putting an L for x would cancel here, and you would have y2 minus y1 plus a y1. So that's just y2 minus ln. And if you put in a 0, then you're just left with y1. And taking advantage of the property of logarithms, which is when you subtract two logs, you can write it as a quotient. And let's see, I don't see anything else that might simplify. So let's take a look at their solution form. They have the rho and the L and the natural log y2. Yeah. Okay, good. Then we get the same thing. So that's what they're after.
Yeah, I think it's interesting too, for your earlier video, but you can see it for this example as well, that because our u sub equation is also the same thing as our y equals equation, like representative of the height.
Yeah.
If we were to substitute in the like bounds of integration into the actual thing, we would see that like it's just a switch of variables. Instead of 0 to L, we'd be integrating from y1 to y2. And it's like, yeah.
Okay, yeah, I do see that. Yeah. I'm not sure if there's any great physical insight to it, but I see the math of it, because basically we're doing a u sub with the height of it, and the height is the y.
Well, I was thinking like if you could know that, if you already are in a situation where it's like you have set up your y equals equation, relating like y and the x distances, and your u sub happens to be in the same equation that your y equals equation is, then you would automatically know that instead of integrating from this x value to that x value, you would automatically say, oh wait, it's y1 to y2, and you don't actually even have to plug in. You could just intuitively say, okay, we're subbing in for like the y bounds instead of the x bounds.
Yeah, but if I'm following that right, I would be a little cautious because see, this only worked because back here, our height was the y variable, and that's what we're doing our u sub for. But there are many problems where the area isn't necessarily connected to the height of our y function, and so you're not going to get that. In fact, I would be a little surprised if that's what you got in 56, but I'm not 100% sure. But because you have the area, which is related to the radius squared, not just the radius, you don't have a linear downstairs, you have a quadratic downstairs. So I don't think it'll work out so pretty in general. So yes, it does in this one because we've got a linear connection between X and Y. We got a straight line that we're, connecting to. But anything that wasn't a linear relationship, I don't think would come out that way. So
okay.
Plus, actually, and another thing is, I think that could be a set of recipes for, students already have troubles confusing the direction the current goes and the area. And if I switched that on them on a quick, easy way to do it, that might just add to their confusion. So I'm not strong advocate for that one. But yeah, but I again, it is linear, so it does work out in this case.
Cool. Yeah. Yeah, that was probably the